As planet Earth spins on its axis, we only ever see the one side of the moon, almost as if it's a 2D cardboard cutout hanging in the night sky. So, why don't we ever see the dark side of the moon? And no, we don't mean the Pink Floyd album. Welcome to Factnominal, and we're getting into the science of why we don't see the dark side of the moon. The first thing to understand about the dark side of the moon is that it isn't really, well, dark. It gets plenty of sunlight, just like the blue marble we're sitting on right now. The only reason it's called the dark side of the moon is because it's impossible to see it for us. Well, that was the case until 1959, when the Soviet Luna 3 spacecraft gave us a permanent photograph of what this mysterious area actually looked like. It wasn't until 1968 when the Apollo 8 astronauts became the first humans to ever see the far side of the moon in person. What's interesting is that until January 3, 2019, all landings on the moon actually took place on the near side, the cycle being broken by the Chang'e 4 spacecraft. So then, why can't we see it? According to John Keller, the deputy project scientist for NASA's Lunar Reconnaissance Orbiter project, the moon does rotate, but it rotates at the same speed as it rotates around the Earth. This means that, in practical terms, the moon is tidally locked to the Earth. In the time it takes to completely orbit the Earth one time, the moon makes a complete rotation around its own axis, thus meaning that the same side is facing us 24/7. The moon has a natural tendency to spin faster, however, it's the gravitational field of the Earth that keeps it in place and in a tidal lock. Think about it like how a car tends to drift when it turns on a curve. The friction of the road stops it from drifting further. This seems a bit too convenient, right? I mean, for the moon to be in a perfect tidal lock, it would have to be the exact right shape in order for Earth's gravity to act in the specific way that we observe it to. Well, it turns out the moon wasn't always the same shape we see it today. A long time ago, scientists believed the moon had its own spin and, over a long period of time, frictional forces, including the gravitational field of the Earth, actually molded the moon into a more spherical shape. However, the moon isn't exactly a perfect sphere. If it were, then the far side and the near side would both experience the same effect of Earth's gravity and would hence cancel out. Since it isn't a perfect sphere, what ends up happening is that a similar portion moves toward the Earth as it spins, while a larger portion moves away. Since the resulting distribution of gravity is uneven, a torque is created that springs the moon back into place. This motion is referred to as lunar libration, and it also explains why the size of the moon appears to change over time. In fact, due to libration, about 59% of the moon's surface is seen over time due to a perceived wagging effect that ends up showing more than just one hemisphere. In fact, libration allowed early astronomers to actually identify a land feature of the far side of the moon. In 1906, Julius Franz identified what he called the Mare Orientale, a prominent impact basin that spans almost 1,000 kilometers. The far side and the near side differ more than just their names, however. More recent images of the far side from missions such as the Lunar Reconnaissance Orbiter have revealed to us the exact nature of the far side of the moon and how it actually differs from the side where we've gotten so used to seeing. For one, the far side is actually older in a sense. It's a widely held belief that the moon was molten when it first formed, later cooling down to a more solid state. It seems that the far side actually cooled down first, meaning it has more craters. As a result, the far side has far less maria, plains on the moon that early astronomers incorrectly thought were seas of lunar water. The far side has only 1% of its surface covered by this maria, while the near side has around 31%. A strange phenomenon that the Lunar Reconnaissance Orbiter team have noticed is that the near side of the moon seems to have more radiation than the far side, which can easily explain why it took so long for it to cool down. However, the team doesn't have any idea what could have caused this bias. For one reason or another, one side was favored over the other. Other popular theories have been proposed that seek to understand the differences between the two sides. One such theory suggests that the moon once collided with a smaller companion moon, explaining the size difference between the two sides. However, analyses of this far side of the moon suggest that no collision ever happened, and that the size and terrain differences simply developed naturally. New research has proposed that the crust on the far side is much thicker than the near side. Meteorite impacts would thus have a stronger effect on the near side that would create Maria, while the thick-skinned far side would simply brush the impacts off as a flesh wound. There is still much to be understood about the origins of the moon and the exact differences between the hemispheres. Which side of the moon would you prefer to live on? The rocky, craterous far side, or the flat, smooth near side? Let us know in the comments below. If you enjoyed this video and want to make sure you never miss another one of our space videos, make sure to leave a like and subscribe to our channel. Who knows what you'll learn next?